Hello again, everyone. It is my pleasure to introduce to you Arefe. I had the pleasure of meeting her back in June in Trieste, but unfortunately, I could only see her work presented in the form of a poster. But today, it is again my pleasure to introduce her to you. And again, what she's going to be talking about is addressing the dipole tension via clustering and long mode modulation. Arefe is a master student, but probably soon to be PhD student. Currently, she's studying at the Sharif University of Technology, and probably very soon she'll also be studying PhD. But the future will surely tell us. Right. So please feel free to start, and ladies and gentlemen, Arefe Rasouli.
Thank you, Nico, for your kind introduction. I'm very excited to be here and talk about dipole tension using the clustering dipole and long mode modulation. This work is a collaboration with Chantal Bapan, Sohab Rahbar, and Hamid Tadayeri. I will start with reviewing a few articles about the dipole tension. Then I'll talk about our method in order to test the ΛCDM model and how we can find NVSS dipole. And then at the end, I will introduce a long mode modulation and a model which will produce an intrinsic dipole in the distribution of our sources. I start with the cosmological principle, which is based on the fact that the universe is homogeneous and isotropic on sufficiently large scale. As we can see in this left map, which is the temperature time of an observer in the CMB's rest frame, but we are in motion with respect to this rest frame, so we will see the right map with a dipole in it. And based on this dipole and using the relativistic Doppler effect, we can compute our velocity, which is approximately 369 kilometers per second. This velocity includes different components. As an important example, the sun is in motion related to the Milky Way in the opposite direction of the CMB dipole that we observed. So as a result, the combined motion will create a velocity around 600 kilometers per second for the local group in the CMB rest frame. In the other hand, the ΛCDM model predicts that as we see the larger scales, the rest frame of the larger scale structure should eventually align with the CMB rest frame. This means we can use matter as traces and escalator distribution in order to find the rest frame and test the dipole as we have done for the CMB. And we can see from this map here, which is the map of number density of the radio galaxies, and it has a dipole very similar to the CMB dipole. And we are going to talk about this dipole in the following. But before that, I want to introduce two physical effects that will create a kinematic dipole in the distribution of galaxy sources. First, we have aberration, which will cause a concentration of sources in the direction of our velocity. And then we have relativistic Doppler effect, which will modify the observed frequency in this way. And then by applying the conservation of photon number, and rewriting the flux density. And from here, we can find the relation between the observed number density of sources and number density of sources at the rest. And by extending this relation up to the first order of theta, we can find the well-known Ellis-Baldwin formula, and we can use this kinematic dipole in order to test the previous assumption about the rest frame of the larger scale structure and the CMB dipole. Here, X and alpha are two important components that can be derived using the flux density threshold of our catalog. In a 2017 study, Colin and colleagues explored the radio galaxy number densities, and they used the combined catalog of the NVSS and SUNSS, and they used the Ellis-Baldwin formula in order to find this velocity field. And their result shows a velocity about 3 to 4 times larger than expected, with a 2.81 sigma deviation from the CMB dipole, which is a big tension. And later in 2021, Secrets and colleagues refined the estimators and applied the Ellis-Baldwin test to the NVSS catalog of the radio galaxies. and the WISE catalog of the quasars, they found these kinematic dipoles for each of them. But before that, it is important to note that a velocity of 369 kilometers per second under the kinematic assumption translates to a dipole with amplitude of 0.47 times 10 up to -2. So in each study, the null hypothesis was independently rejected with values of 2.6 and 4.4 sigma. And as a result, the dipoles for radio galaxies and quasars are consistent with each other. And this consistency improves when they are boosted to the CMB rest frame, assuming the dipole is entirely kinematic. And this suggests that the cosmologically distant radio galaxies and quasars have an intrinsic anisotropy in this frame. Our approach to study this tension further was that we considered the total dipole of the NVSS has three main components. At first, we have kinematic dipole, which we assume that is the same with the CMB dipole in both magnitude and direction. And then we have shortness dipole, which is a random dipole because we are working with discrete sources. And then we have clustering dipole. I'm going to talk about this clustering dipole more and more in the following, but I can introduce it, which is because of anisotropic distribution of local sources around us in the local area around us. And the other important point here is that we have considered a Gaussian probability distribution function for all of these components here. So I want to say that, so we know this kinematic dipole because we assume it is the same with the CMB dipole. And we also, from data analysis, we can find this shortness dipole. And right now we have to find this clustering dipole. In order to find this clustering dipole, we have to expand the number density of sources, which has a dipole in it in terms of spherical harmonics. And then from here, we can find each component of the clustering dipole as a function of this coefficient here, the coefficients of our extension. And from here, we can find the relation between amplitude of the clustering dipole and the angular clustering power spectrum. In order to find this clustering power spectrum, we have to expand and map our 3D density field onto a two-dimensional spherical surface. And we can use the coefficients we derived up here in order to write this relation for the angular clustering power spectrum, which is directly related to the matter power spectrum. In our study, we used both linear and nonlinear regimes to report our results. And for nonlinear correction, we have used the halo-fit model and one-loop model that I'm going to introduce them in the following. And the other important point here is that this window function here is related to the clustering bias and probability of finding a galaxy in a specific redshift range, which is proportional to the redshift distribution. We use the redshift distribution of NVSS sources provided by Cheng and his team, and they derive this redshift distribution by tomography and by cross-correlating between the NVSS galaxy sources and external galaxy data. And we fitted a step function in order to follow our calculation to find the amplitudes for the clustering dipole. So in these two tables, we can see the result of the amplitude of the clustering dipole for both one-loop model and halo-fit model. One-loop model is based on the standard perturbation theory, capturing the nonlinear corrections up to the first order to the density field. But in the halo-fit model, they assume that the total matter is captured in the halos. So we have two kinds of correlations when we have 2 points in the same halo, or we have 2 points in two different halos. So here, both profile and the statistics of these halos are important. And they fit these three parameters using simulation and find correct nonlinear corrections to the linear matter power spectrum. And the difference between these two halo-fit and one-loop model is that the power spectrum of halo-fit model works better in nonlinear regime, and one-loop model works better in the quasi-linear regime. But the results of these two tables are quite similar, because as we consider lower redshifts in our redshift distribution, the amplitude of this clustering dipole increases up to 40 to 60%. And in the other hand, when we consider the nonlinear corrections and we add them to our data, the amount of this change is not that significant and it is very close to the error bars. So in order to have a physical interpretation, we need more accurate data. In previous calculations, we used the power spectrum derived from the correlations at equal time. However, what we observe on the sky reflects our past light cone, as shown here. When we calculate the correlation between points A and B, the structure can evolve between them. This means correlation is not at equal time. Therefore, we can extend the earlier theory to derive a formula with a time-dependent power spectrum here. We also use the geometric mean method in order to approximate the time-dependent power spectrum and simplify our calculations. Here are the results using the time-dependent power spectrum and with unequal time matter power spectrum. The conclusions are the same, but with a lower redshift spectrum at higher redshifts, which slightly reduces the amplitudes when we are comparing these data with data in these two tables. So up to this point, we have these three components of the dipole. So we can compute the total amplitude and direction of the NVSS dipole. But before that, it is also important to consider the correlation between the clustering and kinematic dipole, because as we are in an anisotropic and inhomogeneous distribution of sources around us, they will change the clustering bias as well as they will affect our velocity. So they're correlated and affecting us in the same time. This correlation between kinematic and clustering dipole can modify the probability distribution function of the dipole for the NVSS based on some uncertainties about our data in this way. And we can see that this correlation will shift the amplitude of the kinematic dipole with d of VAD, and as well, it will change the amplitude of the total dipole. And this d of VAD is proportional to the correlation coefficient that I'm going to compute it in the following. But before that, I want to say that here, right now, we have a system in order to find the PDF of the angular distance from the CMB dipole, or we can compute the PDF of the amplitude of the NVSS dipole here. The first important component in order to find this correlation coefficient is the bulk velocity. We can find this bulk velocity using the predictions of the ΛCDM model and by solving the Euler's equation. And we can see in this graph the bulk velocity in each radius of the bulk in, of course, two linear and nonlinear regimes. And as it is shown in the right picture, the velocity difference between these two regimes will decay at around 10 megaparsec over h. The other important component is the correlation between velocity and clustering dipole itself. We can find this relation based on the mathematics we introduced earlier, and we also used the nonlinear power spectrum. And the results for one loop model and halo-fit model are very similar. And we can see that as we consider the lower redshift in our distribution, the amount of this correlation will be doubled at the radius of the local group. And on the other hand, when we add higher redshifts into our calculations, the amount of this change is not that significant for both of these models. The only difference between halo-fit and one loop model is that the power spectrum of the one loop model is slightly higher, which is why the correlation amplitude is higher for this one halo-fit model. So here, the final PDFs are shown in black bars. On the left, we have the PDF of the amplitudes which shifts when we consider the correlation. And on the right, we have the PDF of the angular distance from the CMB dipole. And when we consider when we include the correlation between these kinematic and clustering dipoles, the PDF becomes narrower and it peaks in a smaller angle. Of course, these data are based on this correlation coefficient reported here. Our derived correlation coefficients are reported here based on the halo-fit model and one loop model. And we can see that they are slightly higher than previous studies. So it will reduce the deviation from ΛCDM model to be less than 2 sigma. So up to this point, everything that I have discussed has been reconstruction of the ΛCDM model predictions about the NVSS dipole using nonlinear corrections. Of course, there are another idea that we can address the remaining discrepancy between the observed and expected dipole using the beyond ΛCDM model physics. Here, I used the early universe approach. I apply line mode modulation in the early universe. And we can see that this line mode modulation will modify this initial curvature perturbation in this way. And we can use this modified initial curvature perturbation in order to find their correlation and compute the new power spectrum. So right now, all we have to do is to substitute this new matter power spectrum in this relation and continue what we have done earlier. But the problem here is that we wanted to derive the clustering dipole, which is related to this angular clustering power spectrum at L equals to 1, and which is related to 2 points in 2 different sides of sky. And as a result, when we apply the line mode modulation, we broke the symmetry and isotropy. So these 2 points will not have same power spectrum anymore. And in order to solve this problem, we assumed we choose L's that are large enough that when we are trying to calculate the correlation between these 2 points, they are approximating the same region. And so as a result, they will have the same matter power spectrum. And we also find an upper limit based on the remaining discrepancy between observed and expected dipole in order to, we found an upper limit for this amplitude of the line mode modulation based on them. And here are the final results and clustering based on for the L's higher than 50 in 3 different directions with respect to the CNV dipole direction. And to summarize, we saw that the magnitude of the clustering dipole of the NVSS is very similar and comparable to the magnitude of the kinematic dipole. And we see that as we consider the nonlinear terms and we consider the lower redshift in our distribution, the amount of the clustering dipole increased about 40 to 60%. And we calculated the correlation between kinematic and clustering dipoles with the nonlinear power spectrum, which caused a larger correlation coefficient. And all of these will reduce the deviation from ΛCDM to be less than 2 sigma. In previous studies, in a 2020 study by Secrest, it was about 5.1 sigma. And in the second part, I tried to present a simple model for the case that the part of this dipole be intrinsic. And we try to calculate the clustering for specific L's in this model. In the future, we want to consider endpoint correlations and not just 2-point correlations and power spectrum in order to capture more data. And we can test this method in other catalogs of matter distributions, such as quasars. We want to feed different curves to our redshift distribution, and we can investigate other beyond ЛCDM model physics. And right now we are trying to find a more comprehensive model and to improve our previous model by considering the escape and distance dependency of the sources from this center, which is a Milky Way, in order to do a line mode modulation on this curvature perturbation. Thank you for your attention.